So now we're picking up with looking at some other factors. In the first video, we talked about changing amounts of reactants or products. Now we're going to look at what happens when we change the volume of a container. And so when we change the volume of a container, we actually change the pressure, but not do we just change the total pressure, we actually change the partial pressures of the gases. And we'll look at what happens when we change the volume to change the pressure versus when we add some other substance to change the pressure. So here we're focused on changing the volume. And what I look at is, I say, okay, if I increase the volume, okay, so my volume gets bigger, there's more space, more volume for those molecules to occupy, and so effectively I'm decreasing the pressure, I'm decreasing the partial pressures of each of those gases, and so as a result it's going to favor the side with more moles of gas, because if we've decreased the pressure here, then I want to do a change. I want to favor the side to increase the pressure. And the way I increase the pressure is I'm going to have more moles of gas. Because remember, any mole of a gas under the same conditions will exert the same pressure. It doesn't matter about the identity. It only matters how many moles of gas we have. So I want to favor the side with more moles of gas, basically to restore some of the pressure that I lost from that increase in volume. For a decrease in volume, we're increasing the pressure, we're decreasing the space available, we're pushing molecules closer to one another, and as a result, we're increasing the pressure. And so in order to compensate for that increase in pressure, we're actually going to favor the side with fewer moles of gas. I want to decrease the number of moles of gas and therefore decrease the pressure. So we're going to want to decrease the pressure in that system by finding fewer moles of gas. Now note here that I've specified this as more moles of gas and fewer moles of gas. Note when we look at the example down here, what we see happening is that now we have solids involved. And so when we're looking at this, we only look at moles of gas. So for this particular reaction, we'd only be looking at the oxygen. We're not worried about how many moles of solids we have on either side. Sorry, my slide got a little jumbled when I imported it into the app. So here I'm only looking at the moles of gas here on the left. I have 0 moles of gas on the right and 1 mole of gas on the left. So as I'm looking at increasing volume and decreasing volume, I'm only worried about this oxygen. Because remember, changing the moles of solid or aqueous or liquids doesn't really have a significant effect on the pressure inside that container. So what are we looking at here? So we go back to the same reaction we were looking at earlier. Here we see we have our 2 carbon monoxides, we have 4 hydrogens, and 3 methanols. And now I condense this substance. I make the volume smaller by pushing the piston in. And so I've put these molecules in much closer proximity to one another. And as a result, the pressure is going to increase. We're going to have more collisions with the walls of the container, more collisions with other molecules. And so what has to happen is we want to reestablish that equilibrium. And when I look at my overall reaction, if I look on the left, I have 3 moles of gas on the left and only have 1 mole of gas on the right. And so if I shift this reaction to the right, I'm going to overall decrease the number of moles of gas I have. And so that's a good thing, because if I decrease the total number of moles of gas, then I'm also going to decrease the pressure. And so as volume decreased, the pressure increased, and so I want to do some change to my system that's going to counteract that increase in pressure. So if I look here in the middle panel, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 gas molecules, whereas over here I have 1, 2, 3, 4, 5, 6, 7 gas molecules. So I'm lowering the pressure, so I'm counteracting that. Le Chatelier's principle tells me the reaction is always going to respond to do the opposite of whatever the change did. So on the flip side of that, if I look at what happens when I increase the volume, remember that as I increase the volume, I see that the pressure is going to decrease. And I need to counteract that decrease in pressure by making more moles. I need to have more moles of gas to result in an increase in pressure. So I look here at the beginning, or in my middle panel, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 units of gas. And over here on the right panel, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so now we have more moles of gas. So when there was a decrease in pressure, that was my disturbance to the equilibrium because I increased the volume. I'm going to see that my equilibrium will be reestablished when I make more moles of gas. So in this case, I'm going to be shifting towards the left to make more moles of gas so that I can increase the pressure because I'm trying to get back to that equilibrium ratio, to get back to the right amount of gas molecules. Now, we talked about what happens when we change the pressure by increasing and decreasing the volume of the container, because that changes the partial pressures of each individual gas. And those are the values that we're looking at when we look at our law of mass action. When we look at Kp values, we talk about the partial pressure of carbon monoxide, the partial pressure of hydrogen, and the partial pressure of methanol. However, if we change the pressure by adding an inert gas, so if we look at the system we have up here, maybe we add nitrogen. Remember that inert just means it is unreactive. Sometimes the noble gases are called inert gases, but an inert gas can actually be anything that doesn't react with any of the components. So for this example, N2 is a great inert gas. Another common one we see is argon. Sometimes other gases can be inert gases. It depends on the actual reaction that's happening. We don't see either nitrogen or argon anywhere in our reactants or products, so that's a safe assumption that those are inert. They're not going to react with any of these species. And we actually don't see any effect on the equilibrium because we're not changing the volume. We're not actually changing the partial pressures of the methanol, carbon monoxide, or hydrogen. We're only adding an additional gas, which is not in the overall reaction, so it's not affecting the equilibrium. It's not included in the law of mass action. And because we don't change the partial pressures of our three components, we don't actually change anything about the system. We're not shifting towards the left or the right because we're only worried about partial pressures. Looking at volume, we did have to worry about it because changing volumes changes partial pressures. Adding N2 does not change the partial pressure of any of these components. It may change the total pressure, the sum of all of them, but the partial pressures do not change. So the last effect we'll look at is changing temperature. And we've got a couple of different things we have to worry about. One, are we increasing or decreasing the temperature? And two, is it an endothermic or exothermic reaction? So we have to worry about all kind of four of those combinations for figuring out what the reaction is going to do. So here what we look at is we have our delta H is negative. And remember, is that exothermic or endothermic? Remember, that's an exothermic reaction. That is a negative value, and that tells us heat is being given off. And so what we actually do is show this as a product. And I find this is helpful to students that when you have a reaction and you're trying to look at temperature changes, to not only look at the delta H value, but once you've established whether that it's exothermic, go ahead and write in heat as a product. It makes it a lot easier when we start to see the temperature changes. On the flip side of that, here we have a positive enthalpy value, so we have an endothermic reaction, which means we have to put heat into the system. And so for here, I'm going to write the heat as a reactant. And this will just make our lives a little bit easier. We're not worried about the numerical value of the enthalpy here. All we're worried about is basically the sign. Is it a product, so it's exothermic, or is it endothermic, and therefore heat is a reactant? So let's look at our example. We're going to go back to the reaction we've been looking at here. We have an exothermic system here. And what we have is that we have our carbon monoxide, hydrogen, and methanol. I add heat. Now remember, we said, well, if it's exothermic, that means that heat is a product. So if I ask you what happens when we add methanol, hopefully you would say that we see the reaction shifts to the left. Well, adding heat is no different than adding any other product. If I add heat, I'm going to see my reaction shift to the left. So I'm adding heat, I shift to the left, which means I have the formation of more of my reactants, and I have consumed some of my products. I've consumed some methanol. So heat, because it's an exothermic reaction, is treated just like a product and shifts the reaction towards the left side, towards the formation of more reactants. I can do just the opposite here. I can remove heat. Again, we're talking about an exothermic process. So what I see is that heat is a product. And so if I remove heat, I'm basically removing a product So if I'm removing a product, the reaction is going to respond by shifting to the right and forming more of my methanol. And so here I see that some of my carbon monoxide and hydrogen is consumed and more of my methanol is formed. So adding heat in here, because it's an exothermic, writing it as a product makes it much easier to see what's going on. And when we say we're removing heat, what we're really doing is cooling the system. But remember, I don't add cool or remove cool. I'm really removing or adding heat to a system. So I'm only looking at the fact that heat is a product. So we can go through a similar discussion dealing with an endothermic system, only it's going to be exactly the opposite of what we saw for exothermic. Because when we have an endothermic system, what we're going to see is that the delta H is positive, so now heat would be a reactant, and so we'd see exactly the opposite changes happening that we did for exothermic. So you can put your heat in as a reactant for an endothermic system, and when you do that, you treat it just like you would any other reactant. If I add a reactant, I favor the formation of products. If I remove a reactant, I favor the formation of reactants. So this is going back to our original list here. We talked about changing the concentration of a reactant, changing the concentration of a product, changing the pressure, and we have two ways to change the pressure. We can change the volume of a container, or we can add an inert gas. And so this line here didn't get translated correctly in the conversion to the iPad. And so what we see is that, if I can draw a straight line, is that the addition of an inert gas actually has no effect on the equilibrium because we're not changing the partial pressures of those gases. So changing the volume of a container changes partial pressures. We also see that changing the temperature has an effect on the equilibrium. So now let's look at an example here. So given the following reaction, how could you increase the concentration of products? So we're looking at which type of changes will increase the concentration of products. We're given a balanced chemical reaction. We're also giving the delta H value, so we need to think about whether heat is a reactant or a product. So at this point, pause the video for a few seconds, think about the problem, figure out what the answer is, and we'll come back in just a second to give you the correct answer and explain why it is the correct answer. So hopefully you pause the video and you've gone through the reaction to figure out what changes are going to favor products. And so what I'm going to do is I'm going to say, well, let me deal with this heat issue first. I see that delta H is negative, and so that tells me that heat is a product because we're dealing with an exothermic reaction. And so what I'm actually going to do is go through and look at the factors that they're kind of comparing here. They talk about changing volume, they talk about adding and removing N2, and talk about changing the temperature. So before I actually look at the answers, I'm actually going to go back to my equation and see if I can figure out what a correct answer is going to look like. So do I want to increase or decrease the volume? Do I want to add or remove N2? And do I want to increase or decrease the temperature? So let's first look at the volume issue. So if I want to favor the formation of products, so I want to add more NH3, what I'm going to see is that if I increase the volume, so increasing the volume will decrease the partial pressures, and this reaction will actually shift towards the left because I have more moles of gas on the left than I do on the right. So I see that increasing the volume is not going to help me get to the formation of more products. However, if I decrease the volume, I'm going to increase the partial pressures of the gases, and in order to relieve that increased partial pressure, I'm going to have to favor the side that has fewer moles of gas, so it is going to favor the product side. So I can see that both 1 and 2 are not going to be reasonable answers because I can't have an increase in the volume and favor the formation of our NH3. Now what I want to look at is what happens when I add or remove N2. And so if I look at the addition of N2, if I add N2, the reaction needs to shift to make up for that additional N2, needs to consume some of it. And so it's actually going to favor the right side of the reaction. It's going to favor the formation of NH3. And so I can see that anytime I'm adding N2, that's going to be a good thing if I want to make more products. And so removing N2 is actually going to favor the formation of more reactants. So I know that's not an option. So now I can see that 3 is going to be my answer, but we are going to go on and look at the decreased temperature option so that we can see why it is in fact favoring the formation of NH3. So if I have an exothermic process, heat is a product. I'm going to favor, and if I add heat, I'm going to drive the reaction to the left. So if I decrease the temperature, I'm actually going to remove heat. So I'm removing my product here, and as a result, I'm going to drive this reaction to the right and favor the formation of NH3. And so by decreasing the temperature, I can favor the formation of products. So I don't want to increase the temperature. So I'm going to mark out the 2 increases of temperature. And what I see is that number 3 is the only one where all 3 of these things will result in the formation of more NH3. Now notice that we have the word or in here, and that's because we're looking at these independently. If we start to look at combinations of changes, it's much harder to predict, because if one says we're going to shift to the right and the other says we're going to shift to the left, it's not easy to predict which one's going to have the bigger effect without looking at actual quantitative values. So here we're saying yes, decreasing volume would favor products, adding in 2 would favor products, and decreasing temperature would favor products. And we're assuming that each of those factors is done, or each of those changes is done independently. So that finishes up the content from chapter 14, and that's actually where the exam will end on Thursday evening. On Wednesday, my plan is that we will answer questions that students may have. I'll put a post up on Piazza later today where you can post potential questions, and then we will, on Friday, we'll pick up with chapter 15 and begin talking about more equilibrium, this time dealing with acids and bases. If you have questions about any of this, please post them on Piazza. I will be monitoring that throughout the day as well as tomorrow, and answering any questions that students might have. Please note that on the equilibrium problems, it's most helpful if you can include your work. Ideally, a picture of your work. When you try to type in the equations and ice table, it gets a little crazy. You're welcome to take a picture of your work and post it there with your question so I can see exactly what you've done, and that makes life much easier for me to figure out where any problems may have occurred.